So what are we gonna do is a little bit like Laplace transform. Okay, so when you use, so remember when you used to have Laplace transform from differential equations. Maybe I'm gonna do it on the other video. So I owe you a video, so I'm gonna do a little bit of review on Laplace transform. But so for Fourier analysis, this is kind of the main idea we're gonna do. So suppose you have the partial differential equation. You have u dt equals c ux x, then ux0 equals f of x. Okay. So what we're gonna do is reduce this partial differential equation to an ordinary differential equation problem. So what we're gonna do is apply the Laplace transform. I'm gonna call it like this, right? So it turns out that this problem depends of x and t. And this one is only depends on x. Okay. And this is xt and xt, but I'm not gonna write it all the time. So you take the Laplace transform, so you get capital U of t equals minus c chi square u. So this is, I'm gonna explain the whole process. Okay, this is like the summary. Okay, this is just the summary of the whole thing we're gonna do, and we'll see. I have enough time to do it today, but you'll see that this is very standard and very easy procedure. Okay, so then you get this one. This becomes capital U k0 equals f of k. Okay, so k here is a constant, k constant, and your variable now is t, so you have ut, ut. So this problem now is an ordinary differential equation. This is an ODE. Okay, that's an ordinary differential equation. So now you can solve that one by your ordinary differential equation class. So you do, if you solve it, it's just ukt equals f of k e to the minus c k squared t. Okay, so this is just a constant. This depends of the t variable. This is a constant. So this is, so what is the Fourier transform doing? And that's what everybody loves it. So Fourier transform is killing your x. Okay, so, and actually k should be better called like w because it's frequency. So it's like the Fourier transform takes a picture of the problem in a certain frequency. Okay, then take it over here, and then once you have your ODE, you come back by the Fourier transform inverse. Okay, and when you come back with your Fourier transform inverse, you will use the convolution thing. That's what who talk about convolution? Lee, you talk about convolution, right? And also Patience is going to talk about convolution. Oh, maybe no, she's not. But another statement that after the statement that she does, there is another statement that talks about convolution. I don't remember if she talks about convolution or not. But it's very common to use it for approximations. So once you do Fourier transform inverse, you'll find that the formula that we use, that I have been telling you from the beginning, is this one: uxt equals 1 over square root of 4 pi t, and this integral between minus x minus y squared exponential for ct f of y dy and that's your solution. So you see, you got a detour. Okay, instead of finding the solution directly, you use the Fourier transform to get it. Okay, and this is very powerful. So actually, for example, Jose Galarza, he's gonna talk about a little bit in his defense about this guy, because when you are doing random walks, you can deduce the kernel of the heat equation, or you can associate that to diffusion. Okay, so this is associated to random walk, diffusion, probability. So this is a whole universe. Okay, this is also the Gaussian. When you said in statistics that everything, the central limit theorem. So you said that everything becomes normal distribution. So that's here too. So you see, you had heat transfer, you had Fourier transform, you had random walk, probability, central limit theorem. This thing is gold. Okay. So that's not good if you got a master and you never saw this before. You had no idea what is this expression, and you got a master degree and you don't know, so you were never exposed to random walks or heat equation or PDEs. So you just know convergence dominated theorem and you don't know how to associate it with. So you are like only have one leg. So you need two legs. Okay. Well, you can manage to have only one leg, but it's fundamental. Okay. So this is fundamental. This is gold. And so that's when you go to a talk, people always try to connect with something that people should know. So you should know this formula for random walks, probability, limit theorem from statistics, or heat equation from partial differential equation. So people sometimes said, okay, this looks just like the Fourier transform. This looks just like the heat kernel. So you need to know something so you understand, you connect to something. Okay. So for that, to go this step, we're gonna use two things. This step requires the theorem of convolution plus the Fourier inverse theorem. And I can tell you very fast what are both. Okay. Okay. So I will show you what do they mean. And also here we need some properties of Fourier transform. So we need like three things. And then you can just all these problems look very similar. Okay, so let me start saying what is the Fourier transform. So definition. So the Fourier transform of a function of two variables. So this is a function of two variables, right? Because most of the time people talk about the Fourier transform of only one variable, but so you just keep t like a constant, like a parameter, right? With respect to x. So you are taking the Fourier transform with respect to x, no respect to t. Is denoted by so Fourier transform of uxt equals and this is gonna be 1 over square root of 2 pi of the integral over r of e to the minus psi x uxt dx. So all that you are doing is you multiply times 1 over square root of 2 pi, so things get normal. So they will just get nice expressions. Okay, and then you take the integral and you multiply times e to the minus I. That's the Fourier transform. So Laplace transform So I will do some connection with the Laplace transform. So the Laplace transform just don't have I, okay? And then Laplace transform, you guys just can take a look to your notes of differential equations. So it looks like it's really old, but I promise you, you start looking. Now that you are experts of integration, all that is going to look easy. Okay, so that's a great tool. So that's, and then we're going to use this notation. So I'm going to use, this is the definition. My Fourier transform is just going to be U, and I use this variable and T. So T is just a parameter. So forget about T. You can even not write it down. Okay, but well, no, you keep it, because that's gonna be the ordinary differential equation. But you see, you are keeping this psi is here. That's your frequency. Okay. So you see, and also that's another reason to do this, because it's connecting with physics and waves. So psi is real. Okay, so let's see so this might be probably the homework. It's really easy, but let me do this one. Let's take, for example, the Fourier transform of the partial derivative of u with respect to t. Okay, so this is, what is that? So all that we had to do is take 1 over square root of 2 pi integral of what? E to the minus ixi, and then derivative with respect to time of u of xt dx. Okay, so what do you think we could do? Suppose you are an engineer or a physicist. What would be the easiest thing to do? You don't even know, if you don't care if it's right or not, but you just want to get a formula. So what would you do? Yeah, take the derivative outside. But we know measure theory, so we know conditions for this to be true. So question, can we do this? Can we take the derivative outside dt of 1 over square over 2 pi of e to the minus ixi uxt dx? Okay, the answer is going to be yes. Okay, but as I told you, today we are engineers, so today we have been caring too much about this. So on Tuesday we take care of this. So what is this guy? What is 1 over 2 pi integral of e to the minus ixc uxt dx? What is that? Is that the definition of what? What is that? So look at this. The Fourier transform of who? Of u. Exactly. Oh, thank you. So also a warning. Depending the books you read, they might have the square root or not. If you don't have the square root, you have to put 2 pi on the over here. Okay, so I don't like that definition. So depends on what you use, but it's nicer because then you don't have to, in this form both the Fourier inverse and the Fourier are gonna have 1 over square root 2 pi. So this is gonna be derivative with respect to time of u of xt. So this is great. So the Fourier transform of this guy is just this guy. Okay. Sorry, so no x. Instead of x, what should I write? Instead of x, I should write what? This one. The theta. Okay, so here in my drawing I put K, but I should really put the theta. Okay, I think for some reason, I think it depends of the book that I was following. So okay, so we already have one property. So how it's gonna work? So the way it works is I take the Fourier transform in both sides. So I'm gonna put the Fourier transform of this one, and that one becomes this one. You see, we already have the left hand side. Okay. Now we're gonna take Fourier transform of this one. We're supposed to get this number, and when I take the Fourier transform of this one, what do I get? So let's try the Fourier transform of ux0. You take the Fourier transform of ux0, you're just gonna get here u psi 0. So you take the Fourier transform if I take the Fourier transform of ux0, what is this? This is gonna be 1 over square root of 2 pi, right, of the integral of e to the minus ixi ux0 dx, and this is just the definition of capital U psi 0, right? That's the definition of the Fourier transform of U. So we are doing really good. So we already got this guy, because this guy and this guy. So remember I said that my theta is K in this case. Sorry, theta equals K. So it's just notation, but I will see what book I don't know. I think I'm gonna use K later, but so forgive me. It's supposed to be K or theta. It doesn't matter. Okay, so now notice also that if I have second derivative with respect to time, that will be the same thing. I just have to go second derivative, and I just take it out over here. So if I do Fourier transform of the second derivative with respect to time of uxt, that will be second derivative with respect to time of u theta t. Okay, and this is a constant. Okay, so now we're gonna do let's see, actually, let's do this one. Where?
Is that an n or a 2 in the second derivative?
This one?
On the right.
Oh, sorry, 2.
Okay. What kind of derivative is it?
I was thinking that if I should write for the general t, okay. T n, sorry, yeah. So in general, for any n derivative with respect to time, you will take it out. Okay, so now let's do this one. We wanna take, and this is fundamental, because so that's what I wanna teach you this, because sometimes you are working on these functions and you think your functions don't have to be special. Okay, functions, in order to you do real life mathematics, your functions has to be very special, and Fourier transform shows you what property you need, and partial differential equations, that's a fundamental property that you need. Otherwise, you cannot work on partial differential equations. So let's see. So let's take the Fourier transform of partial derivative of u with respect to x. Okay. So by definition, what is this? This is 1 over the square root of 2 pi, right, of the integral of e of minus I xi, and then the derivative of u with respect to x dx. Okay. Okay, so what should I do, guys? So I need a formula. Actually, you know what I need to get, because here is on my box. I need to get something like this. So it will be like, in using that notation, will be I will need zeta squared. Okay. But for the second derivative. Okay. So, but I'm working on the first derivative, right? So I need to recover the u. Okay. So how could I change this partial derivative with respect to x in a u? Huh? How can you change that into an integral that has u? Okay, what is your favorite trick from calculus 3 or calculus 2? What is the integration by parts? So what is integration by parts? So I need to go, so let me just call, I use the same notation always. So u and db. So what is gonna be dv? Du dx, and then b is what? If db is du dx, b is what? This u, right? So sorry, that's what I'm using this, the u bar, so people don't get confused. So what is gonna be u bar? E to the negative ixi. So what is du? Du bar. So negative, what is it? I psi. Right. That's it. So this is using integration by parts. Okay. Remember, I promised you that on Tuesday I'm gonna show you that the Lebesgue integral and the Riemann integral agrees on closed intervals, but also on infinite intervals. Okay. So all this is kind of depends. You have now a secret weapon. So when you need your secret weapon, you take Lebesgue and take the partial derivative with respect to time, or partial, or you can do your limit, interchange your limit with integral or something. But when you need all that you learn in calculus 2, then you put your calculus knife, and then you start doing calculus. Okay. So then by this I got 1 over the square root of 2 pi, and then by integration by part, this is u times b. So u times b, that will be e to the minus ixi times u. But then this is from minus infinity to infinity. Okay. So that's kind of important here. Okay. Then minus the integral of b du, will be u b du. So minus I psi e to the minus ixi dx. between minus infinity and infinity. Okay, so is that right? It's just integration by parts. And here is where the interesting part comes. So if you see, if you put this guy, let's say that I want to disappear this guy. Okay? I want to disappear this guy. What could I say to disappear this guy? Because first, if I put my infinity, you know, e to the minus ixi is really cosine xi plus I sine of xi. So it looks complicated. Whatever in the best scenario, it looks like oscillatory. Okay. So maybe if when I take the absolute value, the limit, it can disappear, goes to zero if what? What would be nice? That u at infinity is what? So we have 1 over square root of 2 pi. Then you know, I have e to the minus ixi, and let's say let me put this for a second like this: u of infinity minus, and here we have a t, right? And then e to the e minus xi u to the minus infinity t. Okay, let's put it here like that, and then minus times minus is plus, and the I psi, what can I do with this I psi? Because my integral is with respect to x, I can take it out. So I psi, and then integral of u e to the minus ixi dx minus infinity to infinity. Okay. So what would be nice? If I want these guys to disappear, what condition could I put? So, and remember my problem is the heat equation. Okay? When I have a problem in the heat equation, suppose I have an infinite cable and I put heat over here. So it's really hot over here, right? What happened on the extreme parts? How hot is gonna be? Almost zero, right? Because this is an infinite cable, right? I put heat over here, so my cable goes here, but after that, this is how hot it is. On the extreme parts is cold. It's basically zero. So I can assume that at infinity on the extreme values of my cable, these values are what? Zero. And that's fundamental in differential equation, in partial differential equation. The boundary conditions, sometimes you call boundary conditions. You want to know what is happening on the ends. In this case, these are zero. So here let's put it in a color, assuming u infinity t, better like this, assuming limit of uxt when s goes to infinity is 0, and limit of s goes to minus infinity uxt equals 0, we obtain that this guy goes away, right? So my Fourier transform of partial derivative with respect to x, of the u with respect to x, becomes the partial derivative with respect to x of No, oh sorry, no, I'm not doing that. Sorry, is I psi. Sorry, no. Is I psi of the integral minus infinity to infinity of u e to the minus I xi dx. Okay, but who is this guy? Who is that guy? Who is that guy? That's the Fourier transform of u. Okay, so in general we'll have the following formula. So you'll need that you will have to put some conditions, but you will have that the partial derivative with respect to u, or the n partial derivative with respect to u of x will be I theta to the n Fourier transform of u, u small xt, okay, or you want IC the n Fourier transform of theta t. Okay, so this is amazing because what the Fourier transform is doing is killing your second derivative or any kind of derivative with respect to x. I'm making it constant. Even better, when n is even, when n is 2, for example, you don't even have complex, and that's good because when we are here, we are taking the Fourier transform. We are taking the Fourier transform of the second derivative with respect to x. So we all obtain exactly what we want on this side. So in particular, the Fourier transform of the second derivative respect to of u respect to x in second order will be I theta square u I theta t, and this is just psi square u theta t. Okay, and that's exactly what I wanted here. So I remember here I just using k, so maybe I should stop using this k and just say theta. So I'm using just theta, just to be consistent with my other notation. So it's probably next class I use k. So okay. So we just did this first part. Okay. So we just take the Fourier, and you can apply the Fourier the same to the wave equation, to heat equation we just did, and Schrödinger equation. So Schrödinger equation, you just put I here, and you will do the same steps. Okay, and it's really cool because, you know, Schrödinger equation is fundamental equation of quantum mechanics. So without quantum mechanics, there are no cell phones. So you guys love your cell phones, I can see. So without quantum mechanics, there are no cell phones. And then from here, with this method, you can solve the Schrödinger equation. Okay. So next step is just ordinary differential equation. So you guys know how to solve that, or do you want me to do it for you? Just like a reminder, just for completion. Okay. So suppose you have a first derivative with respect to t of u equals, and I said psi squared u psi of t, right? So how do we solve this equation from differential equations? So that you only really need 3 differential equations to work. So you just put this one down. So you have u prime over u equals psi squared, remember? And then what do? We take the logarithm, right? And we take logarithm. Oh, well, you can, sorry, you integrate. And in this case, with respect to time. So when you integrate with respect to time, you got log of u equals theta squared of t plus a constant, right? Just integration, right? Now you take exponential in both sides. You got exponential and exponential, and then you kill this guy, and you got actual value u, and then you got e theta square of t. But notice that this theta is gonna depend, this constant depends of theta, because I had that parameter flying around, so I'm gonna put it like e to the c theta. So I'm just gonna call it a constant. So I'm just gonna call it like the way I call it over here. Over here. So I got this guy, you see? Oh, this c is because I had this c over here. So I didn't put the c. So because I didn't put that c, I don't have the c. So for my c is 1 here. So you get this is another. So I'm just gonna call this guy f of theta, but after I combine the actual value with this guy, so I can just write this like u equals f of theta is a constant, e to the theta squared t. Okay. So this is just a constant. So this is a constant, but I wanted to eliminate the absolute value. So I just make a new constant and I call it f of theta. So it could be positive or negative. So I eliminate the absolute value. And then this is my big U. And that's this box. Okay? So done. Already that part. So to go back, I need 2 main theorems. I almost done. Okay, so I have f of theta and e times minus c theta square of t. So I'm gonna write the theorems that I need. I need theorem of convolution and Fourier inverse transform, and they're easy to remember. Okay, they're I'm not gonna do the proof today. Maybe I don't have time to do the proof, but we're just gonna use them. As I said, today we are just engineers. So we're gonna do this theorem. So theorem of convolution. Convolution and Fourier transform. Okay, so suppose that, well, in this case I'm just gonna follow this note. So if my Fourier transform of f of x, I'm gonna call it like f of theta. Okay, so that's very standard. So It's like Laplace transform. Remember when you were talking? So Laplace transform was also good. Laplace transform, you transform the ordinary differential equation in a college algebra equation. You solve your college algebra equation, and then you apply your Laplace inverse transform, and then you obtain your solution. The same route, but instead of using ODE, you use college algebra, and that's it. So suppose this is true, and Fourier transform of g of x, I'm just gonna call it. Oh, sorry, it's kind of confusing. So Fourier transform like this, and Fourier transform of g of x, I'm gonna call it g of theta. Okay. The proof actually is really short, but then, and that's what they call it convolution. Somebody was asking me that you guys use convolution in algebra or topology or somewhere. So convolution, this is why it's convolution, because the Fourier transform is gonna take the convolution, but my convolution defined as the way in Fourier analysis, like the way that Lee used it, right? My convolution is the integral of f of x of g x minus y dy. Okay, that's my convolution. Equals to the product of the Fourier transform. Okay, so my Fourier transform, that's what is called convolution, because it transforms this kind of product in another product. And this one usually you call it like this, theta. So once you take the Fourier transform of f of x convolution of g of x, evaluated at theta, you obtain this. So you are changing this operation, this product operation in the standard product operation. So people love that. Okay. Or sometimes you need the equivalent. So or equivalent. If you take Fourier transform in both sides, this Fourier transform will cancel, right? So you will get Fourier transform. You get f convolution g equals the Fourier transform inverse of f of theta times g of theta, and that's one of the things I need. Okay. And remember, let me remember what is the convolution means. Remember, convolution means f convolution g of x equals 1 over the square root of 2 pi f of x minus y g of y dy. Okay, so it's the same, it's equivalent to say f of y g of x minus y. So you can write it. Huh? Oh, okay, yours. Mine is gonna have it. So mine, I define it like that. That's, yeah, because you were using another book. So for me, so once I define my Fourier transform, my convolution is defined in another way. Exactly. So mine, I had to use in every one 1 over the square root of 2 pi. So when you don't use it, then for your Fourier transform, you have to put e to the minus I 2 pi xi. Okay, so that's something you must be ready to confront when you are reading a book. So for here, so I like this one because everything has 1 over square root of 2 pi. Yeah, thank you for the observation. So it's because I use this Fourier transform, I need to define it like that. Okay. Yeah. So that's a problem when you are jumping from book to book. So it gets a little bit. Okay. So So that's one of the ones that I need. The other one that I need is the inverse function, the inverse Fourier transform. Let me see what I have. I have the proof, the convolution here. So, you know, what it says, the inverse Fourier inversion theorem is called, is that you take the Fourier transform and you take the inverse Fourier transform, then you recover a function equivalent to the one you got, but not the same. But they are almost everywhere the same. Okay, so that's why this. Here we really understand what we're doing. So engineers don't really, for them it's whatever. It's just the same. Yeah, isomorphic. Yeah, because they're in the same class. So this is the Fourier inversion theorem. And with that, we can finish our problem. You see, we just solved the heat equation. This is really important. So you guys should be celebrating or going for a beer or something, because this can be really. You can just go jump and start reading about this, all the possible applications this has. So if F is L1, so we all know that what it means, right? So is the absolute value is integrable, and its Fourier transform is also integrable, then F agrees almost everywhere with a continuous function f sub 0, and this is another standard, notation. So basically I want to say that the Fourier transform of f, and I take the Fourier inverse transform of that, is equal to f sub 0 in L1. Okay, and remember, in L1 we already saw that two functions are the same, are in the same class if they are different only in a set of measure 0. But this is another notation, so you guys get familiar with this too. Another notation. So Fourier transform is usually f hat. So that's another notation. So f hat, and then this other hat is equal to f of 0 in L1. So it's really cool when you go to Paris and then you start reading, because in the Eiffel Tower they have all these names, right? And you see so many names that you know. You see Fourier, you see Laplace, you see all those guys that you know. You say, well, at least I know half of the guys. But all these French people that have been revolutionary. So Fourier has. That's why Fourier is there, because so this heat transfer, he solved the heat transfer problem. Okay, so he's extraordinary in mathematician. Okay, so that's for the Fourier. Let me see if I have time to. So I have 3 minutes. So let me show you how this how will be the theorem of how will you prove the solution of the heat equation in terms of our LP spaces and everything. So how do we connect this with LP spaces? It's not like we're gonna prove it. I mean, we don't have time. But so this will be solution of the heat equation, and that's what people try to do in a PDE class, but in a partial differential equations class at the PhD level. Okay? It's this kind of a theorem that they show. Here I'm not sure John did it. I think he used Fourier series. I'm not sure he. No, but he was teaching Fourier transform. I think he did. He probably proved it here. Solution of the heat equation rigorously. Sorry, I'm not pronouncing right now. That's right. So look at this. So let ut equals uxx ux0 equals to g of x. So you see, this is your initial data. So we're thinking of g of x like this. This is g of x. So that's a good g of x. A bad g of x will be something like this. If you have that point, you have to go to distribution. Okay? So you have to. That's why you need function analysis. That function analysis. So let this consider this heat equation. So remember, this is xt and this is xt. So let the heat equation with g of x being an L2 space. So g of x is a square integrable. That's another way to say it. Then the solution. So let me write it like then the Green's function representation. So that's something you look on the book of Bernard. In your book that you are using in function analysis, you look Green functions. You will find this over there. Then the Green's function representation formula looks of the following way: uxt equals. So they call it Green function because gxyt gy dy. Okay. Because you look for a g that will be a solution of that form. That's really hard to find, but thanks to Fourier analysis we can write it. So that's integral over r e to the minus x minus y square over 4t square root of 4 pi t gy dy. Okay, t bigger than 0. So indeed you find a solution of this problem in terms of your initial data. So you can choose any data that is nice, like L2, and that will be a solution. But you have more, and let me just say this. So you see the solution is stable. I mean, I can say more things. Well, I can say this. Also, limit of t goes to 0 of uxt equals g of x. How do you prove this? With dominated convergence theorem. Okay. So you will recover your initial data. When t goes to 0, when time is 0, you should recover your initial profile. And that's how the heat was originally distributed. Okay. Also, you can say that, and this is kind of a stability, the maximum of x between minus infinity and infinity, t0 bigger than 0 and t. So you take you take two different initial data. Okay, so you said, okay, my initial data looks like this, and my other initial data looks like that. So what will happen to the two solutions? So this is G1 and this is G2. So what it says is that the solution for each kind of problem is going to be bounded by their initial data. Okay, so these are the solutions. So U1xt is how cool this is going down, and then U2 is how fast this is cooling down. So he's saying they are cooling down proportionally in L2 norm to the original distribution of the heat. So that kind of thing is what you want to. That's what you use LP spaces. That's what you use dominated convergence theorem, and you see, and that's the way you combine Fourier transform. So all these things are real use, and they're fundamental. And without these techniques we have learned, dominated convergence theorem, L2 properties, you cannot prove this kind of stuff seriously. Okay, so with that we can stop. So I owe you a video, so I think I'm gonna make a video. I'm gonna decide if I'm gonna prove the equivalence of the Lebesgue norm